about the strange relationship between adaptive control and stability theory. And I'm going to show you many results in this talk. These results are coming from a common work with Miroslav Krstic. Here you can see us in Thessaloniki. And you can find many of the results that I'm going to show you today in this book, which is our recent book about robust adaptive control. But I will show you some even more results, and we'll talk about them. So let me start from the title of the talk. The title of the talk, I didn't know if I should use the word relation or relationship. So I looked at the dictionary. And a relationship is a close friendship between two people, especially one involving romantic feelings. So I said, no, a relationship is not what I'm looking for. But it can describe also two things and the way they are, in which they are connected. So it is. This is what I wanted to say. On the other hand, relation describes the link between people, groups, countries, and the way they behave towards each other. This is not what I wanted. But on the other hand, there is the notion of blood relation. And these are the people who are related to you by birth, your own flesh and blood. And this is, again, what I wanted to say about adaptive control and stability theory. So that's why both words are used, relation and relationship. And it's a strange relation and a strange relationship because it is a relation or relationship of love and hate. I mean, people love adaptive control, but also hate stability. People love adaptive control, but also you can say that somehow hate adaptive control. And adaptive control people many times give the impression that they hate stability theory. And sometimes they give the impression that they love stability theory. So it is a strange relationship. It is a blood relation. It is a blood relation also in feedback loop. I mean, adaptive stability theory gives the language to express itself in adaptive control. But on the other hand, adaptive control gives feedback to stability theory, and we will see that in this talk. Okay, so it is a blood relation in feedback loop. You cannot say who gave birth to whom. They were both born perhaps simultaneously. Okay, so let us go and start with some stability properties which are useful in adaptive control. And I will focus on output stability properties mostly because output stability properties are very useful in adaptive control. So the first notion is the notion of forward completeness. We have a system, as you can see, X is the state, D is a disturbance, and Y is the output. And forward completeness means that for every initial condition and for every input, the solution exists for all times, for all non-negative times. And then we are in a position to define the output map. And then we can define a new stability property, which is the so-called practical uniform bounded input bounded state stability property, UBIPS property. And is the property that the state is uniformly bounded for all times, for all initial conditions, and for all inputs by a function of the magnitude of the norm of the initial condition and a function of the magnitude of the L infinity norm of the disturbance. Another stability property that plays a very important role in everything that we are going to see today is the input to output stability property. This property was formulated by Eduardo Zondag many years ago, and it is the property that the output can be bounded by a KL function of the initial condition and the function of the L infinity norm of the disturbance. So the effect of the initial condition asymptotically fades, while the effect of the input remains. Now you can see here that I define input to output stability in a way that the function gamma, the so-called gain function, is a non-decreasing function, a non-negative and non-decreasing function, while usually people define input to output stability by saying that gamma is a K function. No, we don't want to do that. We want to have a non-decreasing function because we want to allow the identically zero function to be a gain function. So, and when gamma at zero is equal to zero, then we have IOS. Otherwise, we have practical IOS. Another property that was formulated many years ago by Eduardo Zondag and Yuan Wang is the output asymptotic gain property. And here I give the practical output asymptotic gain property. So ultimately, the output becomes less in magnitude than a function of the L infinity norm of the disturbance and a constant. This constant will play a great role in our analysis today. We call this constant the residual, the asymptotic residual constant. And you can see that in the absence of the disturbance, the output enters a neighborhood around zero of radius equal to this asymptotic residual constant. Okay. Now, if you look at the ways that one can prove input to output stability, then you will see that there are not many tools in the literature for proving input to output stability. And some of the tools that exist in the literature are not easy to be applied in many systems. So Antoine, Chaillet, Yuan, Wang, and me tried to find some relaxed conditions in order to be able to prove input to output stability and prove uniform output stability notions as well. And this took place in this paper. And we managed to prove this theorem. This is the most general theorem that I know and the weakest theorem for proving practical input to output stability. Okay, so this is happening. We can prove input to output stability by using a pair of functions, a pair of Lyapunov-like functions. Okay, suppose that the set where the disturbance take values is a closed set and zero belongs in this set. Suppose that you have a pair of functions, Lyapunov-like functions, and the second function, W, satisfies this inequality. You see here, you have a k infinity function of the norm of the output, and you want two implications to be valid. So you want to have in your hands a function, a non-decreasing function chi, as you can see. When w is greater or equal of chi of the norm of the disturbance, then you can see that the derivative of v becomes non-positive and actually negative by this dissipation term, which depends on a positive definite function and w. So w actually is related to the dissipation rate of v. That's the idea. And this function w satisfies this bound, the dissipation rate. We want that to have in order to somehow relate the dissipation rate with the output. But also, we need this. So the W must be non-increasing when W is larger than the disturbance. Now I'm roughly talking. You can see the exact inequalities in the slide, but I'm trying to give you an intuition behind these inequalities. So when these things are valid, then our system is PIOS, and the gain is explicitly given by this formula. Oops, sorry. Yes. When chi is equal to 0 at 0, then you have IOS, because this becomes a function which is 0 at 0. So this stability, Lyapunov-like stability result enabled us to study many things, and we will talk about that again in this talk today. Now, let me go to adaptive control. So, what is the main objective in adaptive control? We have a system, and this is given by these equations here. Xi is the state of this system. Theta is the vector of the unknown parameters, U is the control input, and D is the disturbance. And we want to design a feedback law, a dynamic feedback law, which achieves two things: practical input to output stability and practical the practical U-Beeps property. So we want the state to be uniformly bounded and to have some kind of a nice input to output stability property for the output. Now, sometimes people ask me, okay, why don't you denote by X the state of this system? Well, we don't denote by X the state of this system because the state of this system is not Xi, actually. The closed loop system will have Xi and Z as states. So the whole state of the closed loop system is Xi and Z together. So it's important to understand this. We want to achieve stability properties for the closed loop system. And the closed loop system does not have Xi as state only. So there are these controller states as well. Okay. What is the problem in adaptive control? There is a robustness problem which is known to all people working in adaptive control. So you have many ways to design adaptive controllers for systems without disturbances, but when you have persistent disturbances in L infinity, then there is a phenomenon called parameter drift, which means that some of the states grow unbounded, and particularly some of the controller states grow unbounded. And this is an important problem. And people have worked on this problem. There are many solutions in the literature, but these solutions require more information. You need to have some information about theta or d, about the unknown parameters and the disturbance. So there is only one solution in the literature that requires no addition. There was actually. Now there is another one. So, but there was only one solution in the literature that required no additional information. And this methodology was called the sigma modification methodology or leakage. This was form, this was formulated by Petros Ioannou and others, co-authors, around 1996, and guarantees a stronger stability property than POIOS and PUBIPs. It guarantees a practical input state stability for all states of the closed loop system. So the problem, so this is a very good solution actually, but there is a problem in sigma modification. And the problem with sigma modification is this. The residual constant that I talked to you previously is unknown and depends strongly on theta, on the unknown parameters. Therefore, the residual constant is not assignable because it depends on something which is unknown to us and exists independently of us. So we cannot assign this residual constant. So this means that the output may not be regulated effectively, in an efficient manner. And we will see that later in some examples. So this is a big problem in sigma modification. We may have practical input state stability, but we lose many properties, and particularly we lose regulation of the output. So the idea that Miroslav and I developed for some years now was to create something new. And this new was named the Deadzone-Adapted-Disturbance-Suppression Control Scheme. So we call this scheme DADS. And the first step in developing DADS was this. We abandoned the task of identification. So we are going to have a direct adaptive control methodology. We won't perform identification. And this is not a big loss because identification, particularly when disturbances are present, is not usually taking place. But this has two important results. It allows us to consider time-varying parameters. And moreover, it will allow us to simplify the feedback laws. Second step was to abandon the task of exact regulation. Again, this is not a big loss because, as we saw, sigma modification also loses exact regulation. And we have only practical regulation. Yes, but now we want to be able to assign the residual constant. So we won't lose output regulation. So we will manage to bring the output to a neighborhood of zero of radius assigned by us a priori. Okay. The third step is to use nonlinear damping with a single dynamic gain. And this means that we are going to design the feedback law based on domination, not cancellation. And this is standard in robust control literature. So we're using here ideas of robust control literature. And finally, in order to prevent parameter drift, we want to stop the adjustment when the regulation has been achieved. And this will be done by using a dead zone in the adjustment law. Okay, let me show you that now. Let us consider this class of systems. Now, Y is the state of the system, the so-called planned state, and it's going to be the output of the closed loop system as well. So that's why is denoted by Y. And you see here we have this class of system. UI from I equal to 1 to M are the control inputs. We also have theta, the unknown parameters. We also have D, the disturbances. But you can see here the way that the control input appears in the system. Now, this is a special way which is called this class of systems satisfies the matching condition. What does that mean? If we knew theta, if disturbances were not present, and if we knew BIs, these are again some unknown parameters, the BIs, then we would be able to cancel the effect of theta. That is the matching condition. We would be able to match the unknown parameters. Okay, so D is the disturbance, theta the unknown parameters, B are again unknown parameters, time-varying parameters. We know no bounds for theta, we know no bounds for B. The only thing that we will assume for BIs is that they are all positive. We know the signs of these BIs, the input coefficients. And they are positive, but we know no lower bound. We know that there might be some lower bound for these BIs, but we don't know that. We, of course, don't know any upper bound for the BIs. So we don't know almost anything about theta, D, and BIs. Okay. Our DATS design is a Lyapunov-based feedback design. So we are going to design our feedback by making use of some Lyapunov functions. And the Lyapunov functions that we are using are involved in some assumptions. The first assumption is the assumption that we actually have a control Lyapunov function for the undisturbed system. So we have a control Lyapunov function when all the BIs are equal to 1, when all thetas are equal to 0, and no disturbances are present. So this is what essentially assumption A says. The assumption B says that we can bound these functions phi in this way, and I would like to say that these assumptions are automatically satisfied if you have a control Lyapunov function and a feedback law, a stabilizing feedback law for the undisturbed system. And we have proved that. Okay, let us now proceed and design the feedback law using some lengthy Lyapunov arguments. We design a feedback law of this form. You can see this is an LGV type feedback law, and these RIs are positive functions. They are given here by this formula. So you have an explicit formula for the feedback law. And now you can see the update law. You can see here, this is the dead zone. This is the positive part of this number v minus epsilon. This plus as an exponent means the positive part of this number. So when v is greater than epsilon, then this is positive. When v is less than epsilon, then this is zero, and adaptation stops. So when the Lyapunov function v becomes less than epsilon, we have achieved practical regulation, and then we stop the adjustment. That's what this adjustment law says. Now, let me return to this feedback law. You can see here how Z appears in the feedback law. This is a dynamic gain, and you can see that it appears the controller gains increase as the dynamic gain increases. Epsilon, gamma, C, kappa, all these are arbitrary constants of the controller. The only thing that we want is this inequality here. What do we achieve with this feedback law? Okay. So what do we achieve in this feedback law is shown by this theorem here. We achieve a number of inequalities for the closed loop system. And you can see here, this inequality is an IOS-like inequality. You can see that the output, the magnitude of the output expressed by this Lyapunov function, is bounded by a KL function of the initial condition plus a function of the L infinity norms of the disturbances. Also, we have a function here. We have a function of the lower bound, the positive lower bound of all BIs. Okay, and we have this estimate for the controller state, the dynamic gain. We also have this estimate, this asymptotic estimate for V of y. These are global estimates. They hold for all initial conditions, all inputs. And this function chi that appear in this inequality, in this estimate, is given by this formula, this explicit formula. You can see how the L infinity norms of the disturbances and the inputs appear. Okay. Now, again, let me say that these actually in estimates guarantee to us the practical input to output stability property and the PU beeps property for the state of the closed loop system. But again, as you saw, you see here, we have an asymptotic a gain function which depends on the unknown parameters theta, exactly as sigma modification So the residual constant depends on the residual constant involved in the IOS property depends on some things that we don't know and we cannot assign. Okay. Well, let's not forget the first inequality. And what is this? So when we first saw, when Miroslav and I first saw this inequality, we couldn't believe our eyes. I mean, this is something that holds for all inputs, all initial conditions, and says that asymptotically the output is regulated. And we can make the output enter a neighborhood assigned of radius assigned by us a priori, because this epsilon is a controller parameter. Now, you see here, we formulated earlier the practical output asymptotic gain property in the way that there is a function gamma tilde, the asymptotic gain function. Now we have gamma tilde to be exactly equal to 0. We have the practical output asymptotic gain property with an asymptotic gain function exactly equal to 0. And this new stability property deserves a name. And we call this stability property the zero practical output asymptotic gain property. So this is a completely new stability property. It has not been studied in the literature before. And this is what I'm telling you, that adaptive control affects stability theory. So here, adaptive control gives to stability theory new grounds to be studied and to be investigated. Okay, we don't have only this zero practical output asymptotic gain property. We have something even better that I told you before, because the residual constant epsilon is assignable. So we can achieve regulation, and this parameter epsilon is given by us. It is a controller parameter. Okay, so one might say, oh, but we have sacrificed exact regulation for practical regulation, even the disturbance-free case. That's not completely true, because when we have vanishing disturbance, and if these constant sigma and lambda that I showed you previously, these are technical, this is a technical point, but doesn't matter, they are equal to 0, then we can show that at least one of the following holds. So either the output is regulated exactly, or the dynamic gain remains small in value. So exact regulation is not excluded. And if you see the update law, we have the opportunity to increase this constant gamma in order to be able to increase the values of the dynamic gain Z, and so we can achieve exact regulation. So hopes are still there for exact regulation. Okay, let me show you all these things now. In this example, this is the uncertain double integrator we have a double integrator, two unknown parameters, theta 1, theta 2, an unknown input coefficient B, and a known disturbance D. Let me show you the design of two controllers. The first controller, sigma modification, is this controller here. Now, if sigma bar is equal to 0, then you obtain a standard controller with no, a standard adaptive controller with no sigma modification. This controller guarantees this Lyapunov differential inequality, which shows practical input state stability. Now let me show you the Dutch controller. This is given by these equations here. Okay, let me show you what's happening here. Now, I will show you two cases, the case where the disturbance is absent and the case where we have a sinusoidal disturbance. So this is the controller without sigma, the adaptive controller without sigma modification. You can see that the plant state is regulated very well by the adaptive controller. Okay. When we have sigma modification, that's the problem of the sigma modification, only one of the states is regulated. The other one, it goes even further away from the initial condition. And this is the problem with sigma modification. Remember, here we have no disturbance. Okay, and we cannot achieve regulation of the plant state. Okay, here you can see the Dutch controller. We have actually here exact regulation of the plant state with the Dutch controller because the disturbance is absent. And you see that this response here looks similar to the response without sigma modification. Okay, perhaps one can say, well, okay, but perhaps you pay a price in the control effort. No, actually, the worst control effort is given by sigma modification. For the controller without sigma modification and for the Dutch controller, the control inputs converts to zero, while this is not the case for sigma modification. And you can see here the controller state when the disturbance is absent. All of them are bounded. Okay, what happens when we have a sinusoidal disturbance? This is the response of the closed loop system for the standard adaptive controller without sigma modification. And you can see this picture. The controller manages to regulate the plant state, and there is an oscillation of magnitude 0.2 around 0, but actually this is not the whole picture for this controller because this picture cannot be continued forever. I will show you why next. What is happening with sigma modification? Here you have a large oscillation around 0 for the plant state, for both plant states. Okay, this is not a good result for regulation. And what do we have with that? Here you can see we can achieve regulation for both plant states. There is a very small oscillation around 0. Okay, now let me show you the control input. We pay no price in the control effort. Actually, again, the controller with sigma modification has a larger control effort. The control input for DATS, which is the black line here, is very close to the control input of the adaptive controller with no sigma modification. So perhaps one can say, why don't we use the adaptive controller with no sigma modification? Well, that's why. We cannot use this controller because of the parameter drift. Without sigma modification, the controller state grows unbounded when persistent disturbances are present. This is not the case with sigma modification. The controller state remains bounded. And of course, this is not the case with DADS. Everything, the controller state, as you can see, remains bounded and ultimately constant. Okay, now I guess I have little time now. We have extended DATS, and we have extended DATS in the case where we have states that we do not measure. So we want, in this case, a partial state adaptive control. Or you can see this kind of system with the W dynamics are neglected dynamics or dynamic uncertainties. Okay, we have developed results for this case, but I would like to, since I know that many of you that attend the ISS seminar are interested in infinite dimensional systems, I would like to show you that is not limited to finite dimensions. DATS can be extended to infinite dimensions. So let us look at this problem. We have a heat equation, W. W is not measured. We have an ODE, Y. You can see here the ODE state Y. And you can see there is an interconnection between these two systems. Now, the key thing here is that we know almost nothing about W. We won't assume that we know the constant P, the diffusion constant P. We won't assume that we know this function K here. We only know for K this inequality. We won't assume that we know the parameters theta 1, theta 2. We won't assume that we know L, this functional L here. The only thing that we will assume is this inequality here. And this is the L2 norm of W. And again, there is a disturbance. So can we regulate W if we have this situation where we know we don't measure W and we know almost nothing about the dynamics of the infinite dimensional state W? Well, yes, we can do that. We can design an adaptive controller by using this pair of Lyapunov functionals. This is a Lyapunov function for the ODE system, and this is a Lyapunov functional for the infinite dimensional subsystem. And this is the L2 norm of the state. The DATS feedback is given by this formula. Again, you can see the update law is the same for all cases that I have showed you. We have arbitrary controller parameters, epsilon, gamma, C, B, A, and we can achieve these properties. Here you can see a practical input to output stability property with Y and W as output. Now you can see we have a residual constant here, which depends on the unknown parameters. Okay, that's expected. This was the problem actually of sigma modification that we mentioned earlier. We have these two estimates together guarantee the PU-BIPS property because the controller state and the plant state are both of them uniformly bounded. But we also achieve this zero practical output asymptotic gain property, which says that we can achieve regulation of y, practical regulation of y, but epsilon is determined by us. And as a bonus, we also get this inequality for w. Of course, this inequality for w is the best that can be achieved when y is regulated. Let me show you that. Why? You see here the equation for w. Now, if y is regulated, so if y takes small values but non-zero values, then this term here can become very large if theta 1 is very large. So we cannot control the residual constant for w because theta 1 appears here and theta 1 is unknown to us. But still, we can get this. And of course, you can see theta 1 appearing on the right-hand side. This is a bonus inequality. We can achieve regulation when theta 1 is not very large. But we don't know theta 1. Okay, we have managed to extend that to cases where we have no matching condition. I guess I have to go. I won't show you now these slides. Let me show you another example where we don't have the matching condition. We have this linear system and the disturbance appears here while the control input appears here. Here we have no matching of the input and the disturbance. We cannot achieve all these properties that I showed you earlier. We cannot achieve the zero practical output asymptotic gain property no matter what is the applied controller. And this can be proved for this system. Why is that? Here, no matter what controller you choose, and particularly if you choose a linear controller, you can stabilize the system, but this inequality must always hold because of the structure of the system. So you cannot assign the gain function, no matter what is the applied controller. Even nonlinear controllers cannot achieve something better than that. So what can we achieve here? Okay, so we can achieve to regulate W1, the first state. And if we want to regulate the first state, then this is the Dutch feedback law that does this job. We can achieve these estimates here, which show the practical regulation and the input to output stability, the practical input to output stability property. Now, the plant state is bounded, the controller state is bounded, everything is bounded for all disturbances. So we have the PUB property. Moreover, when the disturbance goes to zero asymptotically, then the whole state goes to zero asymptotically. And let me now make a comparison with a linear controller. Okay, so you see here the state, how the state W1 evolves for dots. This is the blue line. So dots manages to regulate W1, while the linear controller cannot regulate W1. And they have the same response for almost the same response for W2. And this is the controller state for dots. This is the control. These are the control inputs. You can see that does not require more control effort. It's very economical, actually, in the control effort. So this example has been studied with the new results that I showed you earlier about the input to output, the practical input to output stability. And this example, we can study this control system using the result which were produced by Antoine, Yuan, and me, and prove even more properties for the closed loop system. So that's why I'm telling you that stability theory offers the background to study robust adaptive control. If we didn't use this terminology, these properties from stability theory, then we wouldn't be able to express even the simplest objectives in robust adaptive control. So it is necessary. I urge everyone working on adaptive control to study stability theory. Okay, on the other hand, adaptive control shows to stability theorists that there are properties that have not been studied so far and need to be studied because they arise in adaptive control. So they have this strange relationship that I told you earlier. Another conclusion is that DATs can guarantee very impressive, I would say, robustness properties. And this is my personal opinion, that output stability and adaptive control must go hand in hand. This is my personal opinion. I don't want to impose this opinion on anyone, but this is my opinion and I would like to express this. So if you use new stability results, you can study and you can study and gain even more knowledge for existing adaptive controllers. And on the other hand, adaptive control gives new stability notions that need to be studied. That's all. Thank you very much for your attention.